I'd like to welcome everybody in person, especially those of you who are in person, but also those who are online for our colloquium series here at the Institute of Optics. Before I introduce today's speaker, there's a couple of things just by way of general announcement. One of them is check your invite list. There is an extra speaker series from the Rochester local chapter of the Optical Society that you may find. And for the first time in a long time, we're having that series here on campus. In fact, I think here in this room. And most of them here are here on Tuesday evenings. And the reason they're here on Tuesday evenings is so that people from the community can come in, because these are community-oriented lectures, especially for the optics community. So I just wanted to let you know about those so that you come out, you get a chance to rub shoulders with people from local companies that perhaps you haven't met. It's a little different flavor than the Industrial Associate. You get a chance to hear sometimes from people from local companies speaking. Sometimes they have outside speakers. So it's a good chance. It's not usually a really large group. It's a good chance to get together and visit. As part of that series, on March 4th, we're actually having a joint local OSA optics colloquium. So local OSA is coming to us. I'm going to be in the evening like they usually have. We split the difference. And we thought maybe we would, on March 4th, instead of doing our colloquium at 3:30, we're going to do it at 4:30. To give a little bit more chance for the community folks to come in. And then after that, we're actually going to have a meal out here. We haven't figured out who's going to be catering. It'll be dinosaur barbecue or something like that out here in the atrium so that the students that sign up as well as the local OSA can have a meal together. So that should be fun. That colloquium, for those of you who are first and second year who are taking a colloquium for credit, that still counts, of course, once you get the food. So it's a good deal. So I hope but it is something that you will need to sign up for ahead of time, not just sign the piece of paper, because we do need to do a food count for that evening. So that's March 4th. Keep your eye out for that invite. Again, it's not going to be at the regular time. It'll be an hour later, but also here and then afterwards in the atrium. So those were our preliminaries. I don't think there are any other announcements except to take a look on the website, look ahead to our colloquium series this semester. We have a really nice set of speakers lined up. And today, in the cold period, we're having a few more local speakers because they don't have to travel far. Rick Collins, who's visiting us today, just had to travel, I don't know, from across the way or the laser lab, I'm not sure. But he's Tracy High Professor of Mechanical Engineering and Physics in Astronomy, as well as Associate Director for the Laboratory for Laser Energetics. He has an important role. He's going to be talking to us today, connected with an NSF-funded center, the Center for Matter and Atomic Pressures. Rick comes to us by way of a PhD in physics from The Ohio State University. Did I get it right? And from 1989 to 2016, he was in various positions at Lawrence Livermore National Laboratory, including Group Leader, Physics Associate Division Leader, and Director of the Center for High Energy Density Physics, which of course became his specialty, and also distinguished member of the technical staff. There's been a lot of great comings and goings over the year at Lawrence Livermore National Labs. A number of our PhD graduates have headed that way. Ruth has come the other way, and it's a pleasure to hear from him on some of the work that they're doing. Right? Yeah.
Okay, so can everyone hear me? Great. So it's a pleasure to be here, and this is a pretty amazing time to learn about extreme matter and extreme matter science. And you've heard about many of the breakthroughs. Perhaps there's It's breakthrough in thermonuclear fusion. You've heard about that? You've heard about extreme quantum systems, topological systems. You've heard about all of the planets that have been discovered. And all of those really are at the hinge of high energy density science or extreme matter science. And here, this is one. The first slide shows one example where we have an experiment taking place at LOE, the Laboratory for Laser Energetics. So how many of you have been there? It's a great place. So this is an experiment that we did a few years ago. This is where we have a puddle of water, and it's pre-compressed in a diamond cell. And then, so it's pre-compressed to several GPa, Pascal. And then we take tens of kilojoules of laser light, further compress it. We compress it to millions of atmospheres of pressure. And this shown on the left here, the yellow balls are oxygen atoms. They're locked into a periodic array, and purple is hydrogen that's associated. It's floating like a quantum fluid through the oxygen lattice. And that forms a conducting system. It's sort of like a pseudo-solid, and this is the first time this kind of state had ever been, seen on Earth before. In fact, it largely makes up the internal constituents of many of the water worlds that are being discovered today. So that's one example. There are many examples of extreme matter and extreme matter research, and I'm just going to walk. This is like the roadmap for our discussion today. Okay, we're just going to walk through these different examples from really extreme states of matter, revolutionary states of matter, planets, and a little bit on fusion. And so. We weren't the first to start to explore these extreme states of matter. In fact, Fermi, how many of you have heard of Fermi? Okay, so Fermi, many years ago, really laid the framework for how we thought about high pressure systems years ago. And I put Edward Teller here because he's the guy that introduced me to this field. And here, this is right out of Fermi's notebook, where it's log temperature versus log of pressure. And notice this matter in unusual conditions, and it starts at 10 to the 6th atmospheres. So that's 1 million atmospheres. And so you have the condensed state, degenerate electrons. The electrons, as you squeeze things to higher and higher pressure, the electrons get more and more degenerate. And then pretty soon they have very high Fermi velocities. They're whizzing around at relativistic speeds. And then as you continue to compress matter, you overwhelm the chemical, Coulomb forces, and essentially form nuclear matter, and that's shown at the far right. So this, while the numbers weren't quite right, you had a lot of the ideas right, and that's been really the framework for how we have thought about planets and stars for the last 100 years. It actually has all the essential elements up until about 10, 20 years ago. Now, Fermi wouldn't have imagined that we have all these tools to explore these extreme states of matter with. So, and these are several of the tools that we use to explore matter to realize where Fermi was right and where he wasn't. And so we just talked about the Omega laser, the Laboratory for Laser Energetics, but there's the National Mission Facility in California, where I worked for many years, in LCLS, which is also in California, Stanford, and then Pulse Power in Albuquerque. And so just to belabor at LLE, So there's a wide variety, three major laser facilities there. And so that really the hallmark, it came from this place. I mean, the ideas of how you think about advanced optics, quantum systems, came from these two pathways. And then there's a lot of precision engineering. There's several staffs, so it's on the order of 400 now, staff, scientists, and engineers. It's massive. So that's where we really do most of our work, exploring these extreme states. Over the past few years, we've developed groups in experimental HED science and theoretical HED science, and this is really where much of this work that I'll describe comes from. But there's turns out there's HED research going on all over this campus, and so it's in physics and astronomy, many of the engineering, optics, chemistry, earth and planetary science. We go on and on about their contributions. Because of all of this work, we have a more modern perspective of what I showed in Fermi's example. And here I show, again, it's log temperature, now it's log density. And in that space, contours of constant pressure have this kind of a shape. This one contour in the yellow is the contour at 1 million atmospheres or 100 gigapascal. So that's a contour of constant pressure at those conditions. And at those conditions, the external forces overwhelm the chemical forces. Back up. So in the abstract that I send, did anyone read the abstract? Your hands. Go back, read the abstract. Well, you don't have to read the abstract. Just go to the end of the abstract. And it has a link to a video. And the video will do a much better job talking about much of what I'm talking about today. Only the guy that did the video did a much better job. So you should take a look at it. It's entertaining. And he describes much of the physics here. But in essence, 1 million atmospheres is where you overwhelm chemical forces. If you go to higher pressure, 100 million atmospheres, then that's where you overwhelm the intrinsic quantum forces holding the core electrons together, their quantization. And then you have fusion in the upper right and new quantum states of matter down here. And really the way to think about this is all of the physical laws that you learn and are learning have to either be reconsidered or be thought through when you get to these very extreme conditions. So a lot of it's sort of put out in this National Academy. This came out last year. So over the years, we've figured out how to navigate, how to explore these different regions of this phase diagram. And one is shock waves. So how many of you have learned about shock waves? It's good. Okay. So it turns out, so when you generate a shock wave, things heat up. It looks sort of isochoric on this scale. You can also ramp compressing. That's a lot harder. Turns out a lot harder. So that's where you isotropically compress stuff. And it took years to really figure out how to use shock waves, ramp waves, and convergence systems. They all have their own target designs and they all have their own pulse shaping. So it took us a long time to figure out how to really use these different techniques. I'm not going to talk about a lot of them. I'm just going to go through one of them as an example. And that's this ramp compression. This shows some of the papers that led to this. So let's see, a shock wave. If you squish something super fast, that is faster than the speed of sound, launch a compression wave that's faster than the speed of sound, it produces a shock wave. And that shock wave generates a lot of entropy, a lot of temperature, a little bit of compression. Okay, so then if you want to squish something very fast, but you don't want to generate a shock wave, you have to be very careful. So you have to just ping it. It's very small squishing. So you just ping the system so that you get a small compression wave. It's a sound wave. Sound wave moves through the material and it moves at the speed of sound. And then it turns out that if you launch a sound wave, it compresses the air, compresses the material that you're looking at. And because it's compressed a little bit, it has slightly higher sound speed, so you can squish a little bit faster without launching a shock. And then it increases the density and squish it a little faster. You just keep doing that over and over. And you can squish stuff to whatever density you want to and keep the entropy low. And so we learned how to do this with lasers, where we take a laser and we ramp compress the laser in time. That's shown in black. We put it into, we can plumb the light into a gold can to convert it to X-rays. That would generate a smooth X-ray oven temperature. And that would generate a smooth pressure that increases with time. So that's how we sort of develop that. This is an example. This is a movie of target assembly that for an experiment that we did at the National Ignition Facility. So this is the target. It's a gold can. On the side of the gold can is a piece of diamond with several steps. There's a bunch of lasers that come into the gold can that converts the laser, the ultraviolet laser, to X-rays. And that illuminates a small diamond surface. Diamond surface gets super hot, blows off. So here's the diamond blowing off, and that launches a reaction force, which is a compression wave. That compression wave runs through the sample, and remember, so we do it very gently, so it increases in pressure very gently. And then we have another laser called this Bizar laser. It's a velocity interferometer. So it starts in the red, and so the red light bounces off the sample, and it reflects off and measures the Doppler shift of that light. So originally, no Doppler shift, and then as soon as the compression wave moves through the sample and the sample starts to accelerate, this is an interferometer, and so the interferometer just decodes the velocity through the Doppler shift. You map that velocity in function of time for the several different steps. You use the Lagrangian hydrodynamic equations to get the equation stated, or use the stress versus density. That allows us to get the stress versus density for a number of materials. This case shows measuring stress. So stress, we use stress and pressure a little bit interchangeably. I'm a little bit sloppy here, but so stress, for today's discussion, just think of it as pressure. We're really launching a compression wave that's uniaxial. So in this pressure space, we're getting up to 5 terapascal. So 5 terapascal is 50 million atmosphere. I'll try and do this unit conversion as we go along here. So that's pretty high. That's like the center of the Jupiter. That's higher than anyone had ever had a solid around ever on Earth. And so now we're doing this quite routinely. Now, once you get those solids, they're not around for very long. They're around for nanoseconds. So you got to figure out how to characterize them. And I would challenge some of you, if you can do it on a benchtop, I would argue we can do it in a nanosecond. We can do it in a nanosecond in one of these high compression systems. So we have a lot of students and postdocs and scientists looking in different ways to characterize these very extreme states of matter, and from diffraction to Raman's spectroscopies. And again, I'm not going to go through all of these. I'll just show you an example of a couple of these, how it works. The first one is really inspired by work here, Professor Zhang's effort on terahertz generation, characterization. Garrett Bruhag has been working with Zhao to others to try and develop very high power terahertz sources and then use this to characterize samples. I'd say, so he's used a number of different cases where he's short pulse lasers interacting with coils or wires or structured wires. And to date, it's sort of been able to get about a few joules of energy in the terahertz range. So that really sets us up for exploring details of the electronic structure, mapping out the phonon spectra of a variety of compressed solids, and looking at other elements. Another one is diffraction. So most of you know diffraction maybe. So it turns out the structure of matter matters. Okay, so in fact, this is one of our classic examples, carbon, graphite structure. Many of you have used this in your pencil. It behaves very differently than diamond, and that's just because of the crystal structures. And each of these structures has a unique diffraction pattern. So if you bring X-rays in crystal, whether it's powder or not, you can get a beautiful diffraction pattern out, and that allows you to characterize the crystal structure to give inference on the electronic. So to do this in a nanosecond, it took us a long time to figure this out. So there were folks doing sort of nanosecond diffraction on gas guns, and then Dan Kalantar did some of the very first single crystal diffraction measurements on iron, and then we did some experiments on lead. And really, right now, we're able to explore very exotic states, transitions, things with many atoms per unit cell. And it turns out that for many of these systems, you start with something that's very simple, and it can become very, very complex. I'll show an example. But somehow, a structure is able to form something with maybe up to 100,000 atoms per unit cell, and it's able to do that time scales of picoseconds. So somehow, atoms are able to rearrange time scales that seem really even faster than the speed of sound. And something we're really trying to understand. Okay, so I'm going to just walk through a few of these examples. Okay, so I told you about Fermi. This is, if we just blew up that phase diagram that he had, this is sort of what it looks like for any material. This is really a zoomed in version. So this is pressure versus temperature, and often you'll have in low temperature range, you'll have a solid. A solid might have a phase transition or two at low pressure, and then as you go to higher and higher pressure, it locks into a crystal structure that is close, dense packed, and that means that the melt curve is very simple as you go to high pressure, and everything becomes metal. So that's Fermi's picture, and it's derived out of this Thomas Fermi picture of dense matter. And so we've spent the past few years trying to really test this, going after using diffraction to test this. And this is sodium from Fermi, okay, and this is what we know so far. And what has happened, instead of the melt curve going up, essentially, instead of the melt curve going up and being simple, it does a whole bunch of crazy things. Instead of the material becoming simple metal, it essentially becomes a complex insulator. It's topological insulator. I'm going to know what a topological insulator is. 0 hands. Okay, so guess I'm not going to be able to explain it right now. But think about a system which is insulating in bulk, but because of the electronic structure, when you change the dimensionality, so you make a surface, the surface states are conducting. Okay, so that is one example manifestation of a broad class of topological insulator. And in this particular case, you squish sodium, and if you take condensed matter, sodium is like one of the classic materials that you calculate advanced structure because it's simple. It's got 1 electron, and we squish it, and it takes on tremendously complex structures. Electrons get sucked into interstitials, and it has this topological. Now, it turns out that's not the only system. So sodium is one example that we're really trying to understand. It's predicted for aluminum. We've seen it in magnesium, lithium, trying to understand the general behavior of matter as it goes to very extreme densities. It doesn't look at all like Thomas Fermi or Fermi's original predictions. And it could be that every material at very high pressure. It's not limited to the solid. In fact, it's predicted now to occur in dense plasmas. Now, if I go back here, I'll say that in this range, this what we're calling fluid, which is dense plasma phase, it has a tendency to be insulating. So even sodium in the dense plasma phase looks like electrons are so, but we're looking at a bunch of materials. I'll just say the structure of almost everything we look at is more complicated. And so we have a pretty big effort to try and understand general behavior at very, very high pressure. It's more than just crystal structure. Another thing that we're trying to understand is chemistry. So I told you that when you go to 1 million atmospheres, the chemistry can become very, very different. So the periodic table is just have to you throw away the periodic table and figure out how to construct it at very, very high density. One way that we're doing this is using X-ray absorption spectroscopy, which essentially come in with an X-ray, photoject an electron from the K shell, the lowest energy shell. It can either be captured in an edge state or from the bands, or it can go to the continuum. If it's captured these near edge states, you essentially are that's called zones. So the zones allows you to see what's going on with the general wave function in the vicinity of these down states. And the x-axis allows you to look generally across the structure of various universe to give local order, but it also gives temperature. The thing that I'll just mention is that we see the emergence of these pre-edge bands, which are signatures of hybridization. This is now starting to write out chemical laws that enables hybridization at extreme densities, essentially following these X-rays systems. Okay, so what I guess so I've shown diffraction and this X-ray absorption. The thing that really limits a lot of those is just the fact that we don't have any, the X-ray sources that we have are pretty crappy. So I mean, we take a big laser and we whack a foot. It's not very sophisticated. That's what we do. And it generates a lot of X-rays, you know, we can get 10 to the 18 X-rays in the pulse. But that's, it goes 4 pi and it's pretty broad. So we're developing ideas and ways of generating more sophisticated electrons using an electron accelerator and quantum scattering off of laser. There are a bunch of ways that people are working to do this. We're trying to develop this so we can do it on a single shot in one of these research experiments. Okay, so quantum matter. Okay, what's quantum matter? I showed you one of the topological insulators, quantum matter. What's quantum matter?
All matter is quantum.
Huh?
All matter is quantum.
All matter is quantum. Yeah. So, you've heard about the de Broglie wavelength. So, and if have any of you read de Broglie's original thesis? He sort of goes through and tries and lays that out. That was a good thesis. You should. That's intimidating. Okay, so essentially what he did was he came up with this relationship that the quantum vibration of systems is Planck's constant, and Planck was just developing this at the time, and divided by momentum. Okay, now it's not really clear what to use for momentum. Theoretically, he derived this through relativity ideas, but what we do most of the time is we use the thermal momentum, electrons, protons. And so if you do that, if you just say, okay, the thermal de Broglie wavelength, Planck's constant over this square root of mass and temperature. When that gets to on the order of an interatomic spacing, that's when things get really quantum. And so for electrons, usually you do that with electrons. And that's when that happens, you get conduction electrons. In the case of ions, it's a little more challenging because mass is 2,000 times greater or more. And so it's hard to get quantum ions. But so you notice this temperature dependence that can go to T close to 0, that swells this Broglie wavelength, swells it so that it's larger than the interatomic spacing. And for the case of helium, at 1 atmosphere, that's 9 angstroms, and at 2 degrees Kelvin, the wavelength is 9 angstroms. This is actually where I did my thesis. And in some sense, it's that was the one system we had to explore quantum behavior. Now, with high energy density science, we just take the atoms. We don't really care what the temperature is like. We just take this nearest neighbor distance. We just squish it. We squish it to the point where it's comparable to the Broglie wavelength. And so that unlocks a wide variety of exotic behavior. We don't really understand a lot of what we're seeing, but we're working on it. So one of the classic cases that we're going after is trying to understand hydrogen. Hydrogen is a classic case where it's predicted at 20 megabar, 20 million atmospheres, to be a superconducting superfluid, because it essentially at those conditions, even up to 1,000 Kelvin, has this kind of. This is the phase diagram of hydrogen. This is put out by David separately. And so it's temperature versus pressure. Notice the gazillion changes in the axis. It's not very intuitive, but what it does is it allows you to see the cryogenic behavior, and it allows you to see the solid when the solid rolls over. And this is the region which would exist if you were able to. You're able to get to this kind of behavior. Squish it so that the Broglie wavelength is so that's what we're trying to do. We're trying to get to that yellow region. And so we use these ramp compression techniques. Now, it turns out hydrogen is really squishy. So it's hard to squish slowly. It's really hard. So most of the time we launch a baby shock, stiffen it up, and we compressive slope. So that's been that's the way we've been doing it. And so here are a bunch of examples. So we did early experiments a few years ago, where we take a liquid deuterium and then we ramp compress it. We launch a shock wave and then we ramp compress it. It undergoes an insulating to conducting transition. Notice it gets pretty hot. And so it's not really clear that it'll ever reach this, even by the time you get to pressures that are you can do that for you. And billion atoms. Okay, so that would be pretty hot. That'd be hard to do. So we're developing ways to get to lower and lower temperatures, so that we keep the material solid and access this much lower pressure. So that's a major strategy of what we're doing. This sort of shows an example of where we are. These ramp compression waves, as you compress deuterium, it goes from insulating, it becomes, we're using red light, it becomes opaque to red light. Then, and then as you keep squishing on it, the higher pressure at modest temperatures becomes a conductor. We also did this with hydrogen. Notice there's a shift, that's a quantum shift in the behavior of hydrogen versus deuterium. And what this shows is the melt curve, which is shown in blue. And the two paths, these are the different ramp compression paths, green ones. The gas curve and the solid curve are two different initial conditions. But in almost all of the cases, the lowest temperature we can get so far right at this solid boundary. So we're working really hard to get under the solid boundary. In other words, if I go back here, so what we're trying to do is stay down here so we can get into the secret. To do that, we have a bunch of folks working on ways to create a solid phase first. Then turns out hydrogen has a bunch of quantum spin states. So we manipulate the spin states so that it's in a low entropy, and then we launch the smallest previous compression wave initial shock that we can. When we add all of these things up, we're sort of able to get on a very, very low isotope. So in the next year or so, we should be able to access this range. And so we're developing a whole bunch of different experimental techniques. So this is street optical pyrometer, which will allow us to do reflectivity measurements and Raman so that we can measure whether it's a molecule or an atom at the temperatures. Okay, so there's a whole bunch of stuff that we're doing at low temperatures. But when you go to higher temperatures, it's also interesting. So one of the things that happens when you launch stronger and stronger shock waves, so it gets hot, and you reach this region where the thermal temperature is comparable to the Fermi temperature, which is sort of comparable to the Coulomb energy. And it turns out we just recently discovered it's also comparable to the plasmon energy. The plasmon. It's just like it. But it's in a plasma. So it's the sloshing around of electrons in or phonons. So you have a plasma and it just these electrons slosh around. And they behave just like phonons in a crystal. So we characterize them that way. And we were able to sort of figure that out. But, so unwrapping that story, Amalia, so there's a whole bunch of these discoveries we've been making in this warm dense matter regime where all these energies, it's like a symphony, right? It's a symphony in nature. And then you try and take, that's a flute, that was the oboe. So in one case, Amalia, she was trying to get these measurements at the highest pressures in And it just didn't agree with any of the models, except this very, very old model, which doesn't match anything. So there was a quagmire, and you go to all the theorists, you couldn't come up with a rationalization of what was going on. And so Ryan, Master Chengdong's working on this, said, well, maybe it's just sloshing around of electrons, plasma waves. He calculated that out, and essentially it came up with almost essentially right energetics. So the sloshing around of electrons, when it's exactly the same as thermal energy, exactly the same as thermal energy, the Coulomb energy, turns out it becomes a major player. So so there's a whole bunch of new discoveries we're making in that higher temperature. Okay, so I'm going to leave exotic materials. We're going to talk a little bit about planets, stars. Okay, so although Tom, you took a long time taking extra credit. So let's do a little bit of planets. So turns out it's clear to you. You know, you guys seen the Rayleigh scattering in the sky recently? It's been a long time. Which means tonight, when you go out, there'll be stars. Okay. So as we look up, stars all over the sky. And if you were able to sort of look all across the sky, so this is in your degrees versus hours is sort of where we look at half out the sky. You can see the Milky Way, all of you mapped out the Milky Way a little bit, and you can see some of the constellations. See, here's Orion. You guys know Orion. Big Dipper up here, star. So, so you see all these black dots tonight. Wow. But what you won't see are the color dots. Color dots are planets discovered recently. Those planets are, you know, they look like they're all over the sky. But in fact, Kepler one day is just focused on one area of the sky, and it turns out, okay, let's just see how many planets we can find in this one area. So they just kept looking and looking, and it turns out the longer you look, the more planets there are. Not a real big surprise to some of us, but it's still amazing to see. And this shows a preponderance of planets in one area that Kepler looked right by two systems that we might recognize. These color shows where they are in their own solar systems. So green is essentially planets that are inhabitable. So that's amazing. There are likely these habitable planets and habitable zones all over the sky. So how do we understand those, and how do we use optics to figure out which planets to look at, or various characteristics like these might go spot. So it turns out if you take all of those planets, some of them we measure their mass and their radius, and you take the radius and mass and you just plot. It's one of the few things we can measure. You just get all these dots everywhere, and it turns out you can simulate a planet by just balancing equations of state, so pressure, density relationship with respect to gravitational forces. And so that allows you to make a methane planet or water planet. These are just calculational, simple planets. What it shows you is that all of these gives you insight on what's going on in these planets. It also tells you what the internal pressure are. If you look over here, the internal pressures, terapascal. So usually I go through and I give you a quiz on the unit. Terapascal is 10 million atmospheres. This is a billion atmospheres. And so planets, the deep interior, planets that are being discovered today go from millions to billions of atoms. So everything that I've described to you so far and what I will describe is relevant for the deep interior of planets. So I showed you these exotic topological insulators. That's quite likely those things are. Just didn't expect that kind of exotic. So we have a whole crew of people. This is we have this Physics Frontier Center, Center for Matter and Atomic Pressures, with scientists all around the United States and world trying to understand these things. And so let me just give you a couple of examples. So one example is why is Saturn so hot? You stared in the sky, night sky. It would turn out that you had just the very sensitive equipment. You look at Saturn and compare it to Jupiter. If they're going to be the same age, Saturn just looks too hot. That perplexed planetary scientists for a long time. Dave Stevenson came up with the notion that, well, maybe Saturn has hydrogen and helium, which is what these two planets are composed of. Maybe it's just the right conditions that helium stays separated from hydrogen and it drains down into the interior. So we did some experiments where we essentially take a diamond cell and we pre-compress helium and hydrogen, and then we launched compression waves through it and found this reflectance change. I could also plot temperature. A big jump here and a big jump here. And we worked with theoretical initial calculations to help us unravel what this means. Turns out this is in fact where it's nicely mixed here, helium, hydrogen, nicely mixed in the atmosphere, and then deep in the interior of Saturn, it's unmixed, it's really main, and then it becomes mixed again. That's sun pressure. It is within Saturn, probably not, but it should be. So this is just like reaching a condition where helium and hydrogen feel like oil and water. So this is maybe what it would look like based on Saturn, where you have this mixed atmosphere here, and then this whole region essentially is has this helium rain, where because the rain is heavier, you take advantage of this gravitation, potential energy. So that was that explained a long-standing dogma in astrophysics, but no good deed goes unpunished. So Juno, turns out, has been studying Jupiter with unprecedented precision. And now that we have a better understanding of what's going on in helium and hydrogen, all of those, have you guys seen these beautiful pictures of hydrodynamic behavior? Turns out all of that is now a little bit more confusing, trying to understand what's going on and how to interpret it. Let me just, okay, so let me just go to terrestrial planets. We're trying to understand what goes on in terrestrial planets. In essence, why does Earth look different? Venus and Mars. They are neighboring planets. When you look at those, they're very desolate. No atmospheres. They look dead. But it turns out if you, one of the things that they don't have is a magnetic field protecting their atmosphere. And so we think that it's at least important to have a strong magnetic field to protect us against solar wind from our neighbors. And that is, in essence, understanding how that magnetic field is produced, drawing a lot of attention. It forces you, the way we think that our magnetic field is produced is the Earth has a solid inner core and then a fluid outer core. And the condensation of that liquid outer core onto the solid inner core generates heat. Also releases light elements. Those two combine to give rise to convective dynamo behavior. So understanding melting, viscosity, chemistry, all of those are very important. So let's see, I'll just quickly run through this. So Maggie has been looking at the properties of iron, so the deep interior states, the solid and liquid state. She did these really elegant experiments where she launched a shock wave and then she threw in a series of pickets, followed those pickets as they moved through the iron, and that allowed her to map the sound speed as well as Brunei's parameter and also get melting temperature. And what she found is that it's actually the sound speed is quite a bit lower, so that already tells us how we can interpret a lot of seismic data. We've been mapping out the melt curve for a number of materials. Usually I never show plot without error bars, but it's using, so this is the mean melting curves for a number of materials. One thing to note is that the melt curve of iron, while it starts out pretty low, which is good for Earth, ends up getting very steep compared to these different oxides. And what that means is that as you go to higher and higher pressures, so this is temperature versus pressure for iron. This is the melt curve that I just showed you, but over a more limited scale. If you start and you build a terrestrial planet, it starts out very hot because it assembles. And then it cools off in time. And that's where you might get this precipitate of iron and it starts to grow and create this convective. And so understanding this melt curve as well as this time scale is very important. And it turns out that with this melt curve and the Brunei's behavior, what we can say is that any planet that looks Earth-like, that is sort of on the scale, has the same age as if it's larger than 3 Earth masses, it won't have the core will be completely solid. So that would say, well, maybe not look there. That wouldn't be a great place to look for planets that might be detected. Now, one thing that confounds that is the silicate also has this melt curve, which I showed. It looks like it could melt at similar temperatures. So we're trying to understand the conductivity of the silicates. The point is, for the first time, while we have these beautiful satellites, we've never had the ability to understand those satellite data. This is for the first time we're using big laser facilities to really unravel some of those questions. Now, okay, so those show pressures of several tens of millions of atmospheres. We want to go to higher pressures and understand what happens to atoms and cells. We have to use convergent. Turns out that's because if you shine a laser on a planar geometry and you turn up the intensity, you turn up the intensity only so far and launch smooth shock waves. Get to a certain point, you end up launching laser plasma interaction waves, which sprays the energy and electrons all over, and it just preheats the material. Just heat up. So what we do is we use the laser energy that we can, laser intensity that we can. We shine on spherical systems. And then we launch compression waves that move in spherical geometry. Then when they get to the very center, it gets to very, very high pressure. And so we can do that in balls, or we can do that in shells. And so this is an example of a ball, where we just take a plastic ball and we just shine lasers on the outside. That launches a compression wave. So there's pressure as a function of radius. So as the pressure wave moves in, it gets stronger and stronger and stronger. And then it bounces off the center and rebounds. And that rebound gets to very, very high pressure. So now you see we're getting to hundreds of terapascals. That's billions of atmospheres, tens of billions of atmospheres. Very, very high pressure just by going to the end. And this shows one experiment that we did. We just did that. We just we took a ball, put it in the center of one of these gold cans that I showed earlier, and we launched the compression wave, just a single shot. We took a snapshot. So we took a zinc foil, hit it with other laser beams that produced X-rays that shine through this ball. It allowed us to follow the shock wave. The shock wave moves through this ball. And then we mapped the velocity and the density that gave us state mechanical states, pressure, way up at close to 1 billion atmospheres. So that's getting very close to these conditions where the quantum forces of the electrons really have no competing force. They're just knocked out. That's why you end up with this bump in pressure versus densities, because K shell is the interlying electron. Turns out you can go to higher pressure if you go to shells, and that's just because a ball can only compress so far, but a shell can squish to much higher densities. And that has been used for quite some time. In fact, J.J. Ruby and Smith have been working on understanding how to use mechanical models, essentially just following the trajectory of the shell as a function of time and using emission to get pressure as well as mass density. So with these shells, you can get to conditions now. Here we're at billions of atmospheres. So, or even at omega, have a thin shell press. You can get to several billions of atmospheres, many tens of grams per cc, even for plastic. And so that allows us to really understand thin layers that's those thin layers, as you can imagine, a thin metal layer as it's compressed, it's squished to very high density. Now, as the shock wave moves through this gas in this particular shell, what happens is when it reaches the center, it heats up and it gives off a bunch of X-rays. And those X-rays backlight this thin sample. That allows us to explore the atomic physics of that compressed sample. Here's an example. We just spectrally resolve light. If we put chromium here, spectrally resolve the light, right? We're able to sort of measure the 1s to T transition for a bunch of different ionization states. You see that these different absorption bands, different ionization states, moving with time. That's because the shell got to very high density and then it's releasing, it's maxing. And that we're able to sort of map the behavior of those atomic states, function, pressure, and density. What David Bishel is doing is mapping that. So let me just pause here for a second. So when you squish atoms so that they get to super high density, electrons from the exterior plasma gets squeezed into between the core electron and the nucleus. And what that does is it changes the energetics of all of those electrons. So we're able to sort of map that and understand really how many electrons you can pack into a 4 orbit. For the first time, we've been able to do this. Okay, if you want to go to higher pressures, you trade off the plastic shell for fusion. What goes on all the time at LE or the mega laser. So here you have a plastic shell and you put a layer of DT, which will supplant both fuel as well as an layer. And you compress it to very, very high pressures, and you can get this thermonuclear fusion, where E and T fuse to develop energy. That's done all the time also at the National Ignition Facility, California, where then they take this Solron and this capsule, which has plastic or diamond layers and DT on the inside. And in essence, you turn on the lasers, you carefully package the compress this heavy hydrogen fuel, and that is able to be compressed to about 300 billion atmospheres, where the hydrogen goes from about a fifth the density of water to about 1.5 kilograms. So let me just say that by doing that, they've recently been able to get fusion, which we call ignition, where the fusion yield is it needs 2 megajoules of laser light. They're getting out many megajoules of thermonuclear energy, fusion energy. So this is really an amazing first step, all because we're starting to understand how to manipulate pressure higher and higher degrees. And what we're starting to do now, because of this pressure integration, starting to use this hotspot pressure, see how we can essentially use 600 gigabars to drive pressure waves. Okay, we have a big team of people all around the world. You haven't, so again, go back and look at this video. We have a bunch of things going on around the campus, both in terms of various media outlets. We do a lot of simple Atlantic articles and physics today. And, we have a bunch of workshops. Maybe you'll see those around. Please join us. We're developing curriculum, and we have a bunch of videos. Let's stop there. Thanks. Sorry for being late.
I'm sure there will be some questions here. Anybody has any question? Tom has one.
So if you go back to some of the, I'm going to put in scare quotes, the simpler systems, like just putting diamonds at very, very high pressure. Do isotope effects enter into things at all? Do you find different results if you have like isotope pure diamond?
Yeah, so we haven't done a lot of experiments on those. So lithium is one example where lithium 6 and 7 do behave differently. We looked at boron a little bit, mostly for its nuclear reactor. And of course, isotopes of hydrogen. But there aren't a lot of things to look at. So for the boron case, there happens to be an electron capture, nuclear decay for different isotopes. Using boron. Lithium has also, but we haven't done a lot of work on it.
Yeah, the reason I was curious is I mean, there was some work years ago in which people looked at, say, the thermal conductivity of isotope pure diamond, look at the residual photon scattering, and they actually found a surprisingly large effect. But I don't know if anything like that is at work at these very high pressures.
Yes, I do know what you're talking about. And that would be because you end up with these defects in the photon structure. That almost certainly has to happen in our case too. And I haven't really thought about how that beam structure changed. It'd be a smaller fraction.
Jim has a question.
So you mentioned that from going from a compressed ball to a shell, you were able to, I'll call it, engineer the shock profile. Is it possible to become more sophisticated in the geometry and then have additional factors that would help you? I'm thinking of situations almost in an analog to a multi-layer coating where you have concentric shells, and so that the shocks of others are reinforcing themselves as they go in.
Good idea. There's a lot of work on that, it turns out. The multi-shell work using a cascade of shells does provide a pulse shaping pressure to tune the evolution of the pressure, and it allows you to get pressure amplification different impedances. Impedances allow you to tune the mechanical behavior of these compression rates. And I would say right now there are probably many tens of people thinking about that. It's a great idea. The thing that limits that right now is the technology of being able to make the multi-shell systems. So it's quite likely that once we get to the point where we can print things with the precision needed, we might be able to do that. Yeah, that's a great idea. In fact, Los Alamos, another national lab, spends quite a bit of time thinking about multi-shells.
One comment is, there's obviously the shells have the advantage of the three-dimensional, but if you also were to stack planes and do this in a situation, obviously you're going to have a different structure, but you'd be able to at least be able to understand possible geometry in simpler fabrication.
Yeah, just so you know, and it doesn't go unsaid, we do that all the time to pressure amplified systems or to help out with the ramp compression. Systems are very difficult to compress. For example, in hydrogen, using something like copper, which is very heavy, higher sound speed than hydrogen. It allows us to launch a small compression wave. It turns out it's really hard to launch small compression waves. It's hard to turn on a laser and create an ablation that's really small. So we cheat by doing exactly what you're saying. You hit something that's heavy, and then it releases to much, much lower pressure. That's one example, but we also go the other way. That's good.
Anyone on the Zoom had a question? It's your chance to ask a question. Anybody on the Zoom? I had a small question to ask you. That you were saying that if you apply a pressure on a crystal, high pressure, initially crystal maintains the periodic structure. It's more and more atoms are squeezed into the unit cell. Until what pressure you can go until the crystal structure fails? What is that pressure?
It depends on the material. So when a material undergoes a phase transition, then things usually get complicated. Because as you squish the material, usually what happens is it squishes in one dimension, and then the material properties allow it to relax so that it squishes in 3 dimensions. And depending on the crystal structure and the direction that you're squishing, sometimes that can happen, sometimes it's. When it undergoes a phase transition, atoms have to rearrange. You have to rearrange on the time scale of the compression because, and that's why it's amazing to me that we can compress some materials and have them undergo these very complex crystallographic transitions on these time scales.
Yeah, and still maintain their periodic nature.
So
That's kind of, and that I thought by reason, we can go that high in pressure, still maintain the structure, at least that way, but quite an thing.
So for example, in iron, if you compress iron, this is something that confused us for a long time. If you compress it, I'm going to get the axis. It's like the 0-1-1 direction. You can compress it through the alpha to epsilon transition. You might have that orientation. And it pretty much stays a single crystal through that transition. You change the orientation to the next, and you compress it. There's no way for the atoms to rearrange in a fast way. So it becomes nanocrystal. So we were doing some work in diffraction, single crystal diffraction. We were lucky. We were squishing things along one axis that happened to allow this transformation for iron. Sometimes you just never know how lucky you are. So we were reporting this in a number of journals, and a group from Oxford, who we collaborate with all the time, hadn't been able to recreate it. And so they were also looking at single crystals. This is Jim Harlack, who did some very beautiful experiments for his thesis, but could never see the crystal structure once it went through this phase transition. And part of it just turns out that if you take any other axis besides the one we chose,
Yeah,
it becomes nanocrystalline. You can't do single crystal diffraction.